Hi, Chris Kuzmal here. Let's look at Riemann sums using Python code. And the cool thing is that Python code is clear enough. The reason Python is used in education and people like Python is it's there's not a lot of uh, syntactic confusion here. We do need to do this import math, which allows us to use various math functions with which to evaluate our sums as we wish. So we can now just pull in a sine function, a cosine function, and so on. But here's the left sum. The left sum of a function f, where our dx, our step size, the width of our rectangles is dx. We have a starting point for the integral and an ending point for the integral. So this very precisely defines things. It is defined as being the sum starts off as its value of 0, and x is the starting x value, which is here. We established x as being that. And then while x is less than the end value, we increment the sum by the function evaluated at x. And then we increase x by dx. And we continue as long as x, again, is less than the end. And we return the sum that we computed times the width of each of the rectangles. And that's how we do the left sum. The right sum, the code is identical except for one little thing. Notice that the x plus dx, which was after the sum in the left sum, is now before the summation in the right sum. And that's the only difference. So in terms of computer code, it becomes very precise what the difference is between the left sum and the right sum. And then if we want to compute the trapezoidal sum, we can just compute the right sum, compute the left sum, and then find their average, and that's the trapezoidal sum. That's a great way to think about it. But if you want to think about it without the aid of the right sum and the last sum, then the trapezoidal sum, what I call inline, adds f of x before and after incrementing x. And then because it did that double addition, we divide the result by 2. So that turns out to be just exactly the same computation as the trapezoidal sum. And so that's the trapezoidal sum inline. Meanwhile, the midpoint sum is exactly the same. You could actually view it as either the exact same as the left or the right sum. But we increment dx by 2, x by 2 times dx rather than by dx on each iteration. And you might say, well, why the heck would you do that? It seems like you're throwing away information. In a sense, we're not sampling. We're sampling at half the rate in the midpoint summation as we are in the others. And yet it turns out the midpoint summation does a pretty good job of computing the result. And so if you were to offset the start a little bit, then your midpoint sum is going to actually be more accurate than either your left or the right sum. But it's not going to be as accurate as the trapezoidal sum with the same number of sampling points. Okay, so there you go. I guess that's all we'll talk about for today.